You have to make notes of those so that Steve can add them.
Oh, really?
Mm-hmm.
Oh, okay.
Yeah, that'd be really good. Really helpful. Yeah.
Oh, yeah.
Because although this lab manual is like 100 million times better than the one we had before, it's obviously still going to miss stuff. So, but yeah, if you've got like, that would be awesome. That'd be awesome. Okay. Cool. Cool. Oh yeah, so just so it's on the record here, my recording. Like I said, if you do better on the final, right, I'll shift the weight of all the tests, or any test that you do better on the final, then it didn't really work out. Language. So any test that's worse than the final, I'll shift the weight of that test to the final exam. But I can't know that until you've written the final, right? And so, so for now, it's just going to stay steady, and then I look at that after, right? I just kind of shift them over. So, but yeah, I don't know what happened, but it wasn't a very good test for anyone. So, okay. What are we doing? Was there anything that I had to say before we started? I don't think so. Yeah. 48%. It was really bad.
I thought I was reading bad.
I know. Yeah, and what's even more weird is I was kind of like, oh, okay, well, this is my fault, obviously. And yeah, that can happen, right? But then Steve, who's taught it a billion times before, used this exact same test, had like a 48.9 average. So not sure what's going on. No. I don't know. Yeah, maybe. But his class is right after ours. It's still early. Yeah, you're right. I think we're all at 8 in the morning because Joya's section is Monday, Wednesday, Friday, but I think they all start at 8. And then we start at 8, and then Steve's class starts at 10, I guess. Maybe you're onto something. I don't know. But I don't know. But yeah, so, and he said that I gave you guys more hints than he did on what was going to be on there. So I'll keep doing that though, but so. Okay, that's the test. Let's forget about that for a second, because we're about to finish chapter 2, and I am so excited because we're going to be done, well, not done with limits, but limits will be kind of in the past. We'll have easier way to deal with things after today. So in chapter 3, we're just going to do derivatives the way they're kind of meant to be done. But for now, we're just going to trudge through and use the limit definition of the derivative. So, but in 2.7, wow, I feel bad. Get your test back. So what's your name? Jordan, last name? So we've already talked about rates of change, and so, wait, that's bad. Change my pencil here. I like it thick, but not that thick. 2.7 is on derivatives. Oops. and rates of change. Do you guys remember in the beginning of chapter 1 where we said, okay, we've got this curve, and now we want to find the slope of this curve at some point. And so we took 2 points because that's how we draw a line, and then we move it closer and closer and closer. Feels like a limit to me, right? And so we can actually translate that into a limit instead. So when we try to find a tangent line, when we try to find a tangent line to a curve, wait, things are jumping around all over the place in here. Usually it only jumps around if I'm charging it, so I don't know what's going on. You didn't miss anything. I've been blabbing this whole time. So when we try to find a tangent line to a curve, or we also talked about, I don't know if you remember, but we talked about that CN tower example where, okay, we know the speed that it's falling at, right? Or we know the distance and we know how to calculate the distance. And so we can find the velocity of it, the instantaneous velocity, or we pretended to. Again, that's a derivative, which is what we'll call it from now on, or a rate of change. Or the velocity of an object. We arrive at a limit problem. We arrive at a limit problem. And this special type of limit is called a derivative. And this special type of limit is called a derivative. So we'll talk a little bit about tangents, and then we'll talk a little bit about velocities. Tangents. Remember, the tangent is the line that only touches the curve at one single point, right? And it just touches, right? So that's the tangent line. And if we find the slope of the tangent line, then we call that our rate of change at that point. Right? And so if we want to find the tangent line at some point, right, then first we need to find the slope at that point, right? Which now we're going to say, okay, well, we can probably use a limit, right? And but we also need to know the point, right? And then we can use the point slope form of a line to create this tangent line equation. And so if we want to find the tangent line, at a point I'll use x0, y0. The textbook does use x1, y1, but I find it's confusing because my ones look like commas, and so it's just a bunch of commas everywhere. So I'll use x naught, y naught. Why not? Yeah. And usually a subscript 0 we can read as not, like not, null, nothing, 0. So x0, y0, or x naught, y naught is usually how you say it.
Intercepts?
So that's just at any point x that gives some y. So it's just an x, y combination. And so at one point on the curve, right, we want to find this tangent line. So this is just the general case for finding the equation of the tangent line. Then we need to know the point. So if we want to find the tangent line at a point, we need to find the slope at that point. We need to find the slope at that point. Then we can use the point slope form of a line we usually like the slope intercept form of a line, right? Y equals mx plus b, we like that. But the point slope form of a line is more general, and so that's the one that I want you to start using. And we were talking about the lab right earlier, so on the lab final, like clockwork, you're gonna need to find the equation of the tangent line, and it will involve using the point slope form. And so I'll show you how to do that with the derivatives today. But yeah, I don't know where you're at in the labs. I don't get to teach any calc labs. Yeah, nice. I'm glad you guys like Maple. Some of you, maybe more than others. But the point slope form of a line says that if you have a y, any y, minus y naught, right? The y that you know, this point that you know, is equal to m times x minus x naught. Right? This one's worth remembering, memorizing. In fact, well, it's just the equation of a line. So anytime that you've got a line, this is going to be the more general form of that line, right? And I can't remember if we talked about it or if my pre-calc class talked about it, but either way, I feel like this is my pre-calc. If you think about the intercept, right? At the intercept, at the y-intercept, x is 0 and y is b, right? And so if you plug in 0b in here, you can rearrange it to get to y equals mx plus b, right? And so they're the same, but this is the one to log in your brain, okay? Because the slope, yeah. I'll sneak that in here. We need to find the slope, m. So a point, though, if you think about your xy, right? Then, and you've got this curve that you're interested in, right? You're interested in this point, right? Then there's some x naught, y naught, right? Because this is at x0, y0.
Sometimes like we are asked to find the slope at this point.
That's right.
So we will have y is equal to
To find the slope, we're going to use a limit. Yeah. In fact, here it comes. We can now use limits. We can now use limits to find the slope. To find the slope, which I'll put m in brackets, at a point x equals a. So more general than saying x naught, but honestly, it doesn't matter, right? So any point x. By saying that m is going to be the limit as h goes to 0 of f of a plus h minus f of a over h. Clean up my h. Oh. Hopefully that difference quotient looks familiar, right? That's from question 1 on test 1. If I give you a function, f of x, you have to find f of a plus h minus f of a over h, right? And so we're going to be doing a lot more of those. It wasn't that good, but we'll get a lot better at it, right? Because then we're going to let h go to 0, right? Because now you're talking about the point at a, right? And then you've moved out some distance h. Right? And so if we talk about how we talked about it before, oh. So again, if I've got this curve here, here I am at A, and then I move out to some point A plus H. I guess I should have it going straight down, not like that. Right. If we think about the y value here, this is f of a plus h. Whatever a, we've moved out h, a distance of h. And then here, that y value is just going to be f of a. Right? And then we said, okay, well, from this point, wait, here, let's see if I can connect these two. If we need the slope of this line that connects these 2 points, right, the slope, the rise over run, m is the rise over run. Well, in this case, the rise, the distance between f of a plus h and f of a is just going to be f of a plus h minus f of a, whatever those two are. That's the distance on the y-axis, right? So that's your rise. And then your run is going to be a plus h minus a, which is just going to be h. A plus h minus a. And now what we're saying is we're taking that point by taking the limit here, right? Because now you've got f of a plus h minus f of a. So that's the same up here, right? And so that's this distance. Okay. And then you've got a plus h minus a. Well, a minus a is going to go away, right? So then you're just over h. So now the distance here, the run, is just h, which makes sense, right? And so what we're doing, right, to find the slope at this exact point, right, we wanted to move this little dot closer and closer and closer. Well, we can say that by saying, well, I'm going to take the limit as h approaches 0, right? As this distance is going to 0, right? I'm going to get closer and closer and closer to the point, right? And so now, that's how we're going to find the slope at one point, right? Using the limits. We needed limits to get there, right? So I got to put a, this is important, got to put a box around this because we're going to use this a lot. Now I'm so scared. I have to check that I'm not on mute. I'm not. Phew. Okay. It always happens. At least, well, once a term it's happened, and I just can't seem to shake it. Let's do an example so that we can kind of look at this. if I ask you to find the equation of the tangent line, so find the equation of the tangent line to the hyperbola y equals 3 over x at the point 3, 1. And you know that point is on the line, right? Because if I plug in x equals 3, I get 3 over 3, so y equals 1, right? So 3, 1 is on this curve. Just so I can match the notation that I've got up here, right? Instead of using y equals 3 over x, I'm just going to use f of x is 3 over x. But remember, those two are interchangeable, right? So if I give you y, you know, you have f, and then of x in this case, because that's our variable. And so I'm going to say let f of x be 3 over x. Maybe I'll put these down as steps. Step 1, figure out what your function is, right? F of x is 3 over x. Step 2 is going to be to find the slope at the point 3, 1. Find the slope at 3, 1. So we said, okay, well, the slope we can find as the limit as h goes to 0 of f of a plus h minus f of a over h in general. A is the point that I'm interested in. Right? And so here, 3 is going to be my A. And f of a is just going to be f of 3. So that's just going to be 1. But actually, I'm just going to focus on the 3, because often we won't have 3, 1. I'll just say at x equals 4, for example. And then we could figure it out. But I like to have just the general, just focus on the x value, right? So at x equals 3 or at a equals 3. So this is going to be the limit, the limit as h goes to 0 of f of 3 plus h minus f of 3 over h. Right? We don't need a value for h because we're just going to take the limit as h goes to 0. Remember to put those limits on there, right? Until you've actually taken the limit should be out in front the whole time. And that's why mine is so sloppy, because you end up writing it a billion times over. So you'll develop your own little limit squiggle. So now, if my iPad doesn't jump around so much, the limit as h goes to 0 of, well, f of 3 plus h is going to be 3 over 3 plus h, right? Wherever I see an x, I'm going to plug in 3 plus h as its own thing. Right? And so f of 3 plus h is 3 divided by 3 plus h minus f of 3. Now, that's just going to be minus 3 over 3. For these simpler ones, I don't really feel the need to use the big brackets, but once we get into bigger functions, it'll be useful to put bigger brackets around f of a plus h and then f of a. So this is this big bracket, and this is this big bracket. Coming. Good. You could keep it as 3/3, but because you're subtracting two fractions, you need a common denominator. So it's actually going to be easier if you just rewrite it as 1, right? 3/3 is 1. And so what I'm going to do is I'm going to take the time to just take the limit as h goes to 0, keeping that 3/3 plus h, but then minus 1. And I'm going to ditch those big brackets here. It's just to make sure you don't forget anything. So now I need a common denominator. And so what I'm going to do is I'm going to multiply the 1 by 3 plus h over 3 plus h, right? We've been doing that a lot, and we're going to do it a lot more, right? Because we're often going to end up with fractions that we need to add or subtract here, usually subtract. And so just get in the habit of however you want to find that common denominator is fine by me. I always just multiply both sides by each of their own denominator, sort of. So now I have the limit as h goes to 0 of 3 minus 3 plus h over 3 plus h all over h. Three minus 3 plus h, I get negative h over 3 plus h over h. So many h's. So I have the limit as h goes to 0 of negative h over 3 plus h. And then remember that this h is actually h over 1, right? So now you've got a fraction over a fraction. So you're going to flip and multiply, right? And so what I'm going to do, because I want to keep it on the same page mostly, is I'm going to multiply this by 1 over h, right? To bring that h from the denominator up to kind of the same level as the numerator. Right? Oh yeah, so here I've got a fraction over a fraction, right? Even though it's over h, I can always write it as h over 1. Right, so now if I've got a fraction over a fraction, I have to flip this one, but then I can multiply them. And so I've kept this one the same, simplified to negative h. And then I've got the h over 1 is flipped to 1 over h. But now that's how you're going to cancel this h in the denominator. Because that h in the denominator is the troublemaker, right? Because we're taking the limit as h goes to 0, right? But if we're multiplying everything by 0 down here, then we're dividing by 0, which we're not allowed to do, right? And so we need to figure out how we can shake that h down here, and so it'll always cancel out. So now, I didn't quite fit it on one page. Well, I guess I could. This is going to be, if I take the limit as h goes to 0 of negative 1 over 3 plus h, right? I just get negative 1 over 3. But I'll squeeze it in here. The limit as h goes to 0 because I want to see it cleaned up. Negative 1 over 3 plus h. Now, if I let the limit go to 0 for h, I get negative 1. over 3. Which means my slope, right, of the tangent line at x equals 3 and y equals 1, but at x equals 3 is negative 1 over 3, right? So I've got this negative slope. So already I know kind of what this curve is going to look like.
Like, how do you shape the H?
Oh, here?
Yeah.
So if I go,
Oh, no. Oh, but I mean the second last one, the negative 1 over 3 plus H.
Now I'm actually going to take the limit. So that's why I've dropped the limit notation, because I'm going to let h go to 0 because it's safe now, right? As soon as I'm not dividing by 0, I can just let h go to 0, right? But we can't do that unless we're not dividing by 0 anymore, right? And so first we have to get to the point where we're not dividing by 0, which we're at now, and then we'll have a limit. Okay. So therefore, m at 3, 1 is m equal to negative 1 over 3. Or the slope, if you want to use words. And using point slope form, the general form, we've got y minus y naught is m times x minus x naught. The y we know is 1, so y minus 1. And you could easily just calculate, if I only give you a value of x, but I give you the function, you can plug in that value of x to find the value of y, right? And so here, we're given that it's at 3, 1, but we could easily just find the 1. Is negative 1 over 3 times x minus 3. Which now we can rearrange to get into that form that we like, y equals mx plus b. Or maybe I'm the only one who likes it, but anyways, I usually like to see straight lines in the form of y equals mx plus b, because then it's easier to wrap our heads around. So then we have y minus 1 is negative 1 over 3x minus 3 times negative 1 over 3. Y is negative 1 over 3x plus 1 plus 1. And get y is negative 1 over 3x plus 2. So it's still got that same slope that we found, right? But now we know the y-intercept as well as that, positive 2. Nice. So like I said, you'll have to do something similar, but you'll use Maple for the Maple lab final. I know it.
Do mathematicians, when they see this sort of question, do they plug it into Maple? Or do they do it by hand?
Well, so one thing that I was doing a lot in like kind of later in my undergrad, because my undergrad's in math and then I did stats for my master's. So, but if you find an answer and you're like, because you'll get these huge answers, right? Usually in Maple, I'll just plug it in and do this minus this and just hope that it equals 0, because that means they're the same thing, right? And so, so usually, yeah, we end up using Maple a lot, is just to check, because it can handle all these big, and now, I mean, we've got Wolfram Alpha does basically the same stuff, right? And so we can handle all these big equations, but yeah, definitely lean on Maple quite a bit later on. So, and if you do, and I recommend that you do, linear algebra. It's a really fun course, and you get to deal with matrices, and so then you're definitely using Maple to do all these matrix computations. It's really fun. And I think Calc 1 is the only prereq, because I took it to avoid having to take biology. I know, bad, but it's the truth. So, and then I was hooked on math ever since, so. Any questions about this one? All right. First, we have to find the slope, and then we have to find, oh, I guess I should number these. This was step 2, find the slope. Step 3, construct our line. Okay. Let's talk a little bit about velocities then. We said, well, the velocities, and we're going to use that exact same example from section 2.1, where we were just introducing this idea of coming closer on a point, right? And so we can also say from section 2.1, right, if you want to refer back to it, that the velocity at some point A can also be written as the limit as h goes to 0 of f of a plus h minus f of a over h. Does the limit? No, it's just me being me. I think it's because my default writing is actually cursive. Like I handwrite everything, and so that's why my writing isn't that good. I guess excuses. So v of a, right, is the velocity at time t equals a. Because usually if we're talking about distances over time, right, velocities, then the variable that we're looking at is the time. So the velocity at time t equals a is equal to the slope of the tangent line, to the slope of the tangent line. So we're going to use that same example. We've got the CN Tower in Toronto. And so example, suppose that a ball is dropped from the upper observation deck of the CN Tower, 450 meters above ground. Suppose that a ball is dropped from the upper observation deck of the CN Tower, 450 meters above ground. I will put a little side note here. Also, in physics, recall that the distance fallen after t seconds is 4.9 t squared in meters. Right, so recall that the distance fallen after t seconds is 4.9 t squared in meters. We just use this, just because we want to have a function of t. This is what we're going to use for, yeah, so here. And I would never expect you to have any sort of equation in your mind, right? And so nothing even like this, right, on a test that would tell you, hey, here's this equation, use it to find all these things, right? And so here, because it's been established and it's from the textbook, well, I just figured I'd remind you guys. Yeah. Yeah, so we can do that, but now we'll use limits instead. All right. And part A that we're going to answer is, what's the velocity of the ball after 5 seconds, right? So then we're going to use this velocity limit. So what is the velocity of the ball after 5 seconds? And part B, how fast, so what's the velocity? How fast is the ball traveling when it hits the ground? How fast is the ball traveling when it hits the ground? That one's going to be a little bit trickier, right? Because we need the velocity, but velocity, right, is a function of the time. So that means we need to figure out, well, how long is it going to take for it to travel 450 meters, right? And then we can go from there. So for both of these problems, it's going to be useful to know just the velocity function, right, v of a. So we can start there, and so we'll start with part A.
Because velocity is a constant. It's not a constant.
The instantaneous velocity at that exact point.
Oh, okay.
Yeah. We'll talk about acceleration too, because we'll take it one step further. It just means taking another limit. Yeah. The second derivative, which we're getting to. We just gotta swim through these limits first. And so if we know, so knowing that s of t, which is the distance, function of the distance, is 4.9 t squared. How about we let f of t, right? Because it's still a function of t because the variable in there is still t. But just so we don't have to convert our velocity limit into s's, right? I'm going to rewrite this as f of t is 4.9 t squared, right? And this is just to match our general notation, right? If you're comfortable with using s's, that's fine, right? Then you don't have to do this step. But I'm going to use f of t just to simplify it a little bit. So then we said that v of t, so the velocity at any time point t, is going to be the limit as h goes to 0 of f of t plus h minus f of t over h. Which in our case is going to be the limit as h goes to 0 of f of t plus h is 4.9 times t plus h squared minus f of t, which is 4.9 t squared. And again, just to kind of emphasize it, I'll put big square brackets around each of them, just to make sure I haven't missed anything, and then it's all over h. So now I'm going to expand this and then simplify it, and I already know that that h in the denominator is going to cancel at some point, right? And then I'll be able to take the limit as h goes to 0. And so here I've got the limit as h goes to 0 of 4.9 times t plus h times t plus h minus 4.9 t squared over h. Now you guys are probably way faster at expanding these things, and that's great, but I usually like to do all the steps just in case I miss one. That would be bad. 4.9 times t squared plus 2th plus h squared minus 4.9 t squared all over h. Put this on the next page here. So I'm going to take the limit as h goes to 0 of 4.9 t squared plus 9.8 th plus 4.9 h squared minus 4.9 t squared all over h. Usually what happens is that any term that doesn't have an h in it cancels, right? And so that's the case here. So 4.9 t squared minus 4.9 t squared, those go away. And I can pull out a common h from the numerator and say, well, then I can take the limit as h goes to 0 of h times 9.8 t, right? I've pulled out a common h, plus 4.9 h over h. These h's are going to cancel. And now, if I let h go to 0, all I'm left with is 9.8 t. But I'll rewrite one more step here. The limit as h goes to 0, just to show you. 9.8 t plus, I let h go to 0, then I'm left with 9.8 t. So now, the velocity at any time point t, we can use just 9.8 times t. So v of t in general is 9.8 t. The question, though, was asking for, at a specific time point, what's the velocity of the ball after 5 seconds, right? So now we're going to let t be 5 and plug it in. So therefore, v of 5 is 9.8 times 5, which is going to be 49 meters per second. Okay. So that's after 5 seconds. Part B, now we want to know, okay, what's the, like we clarified, the instantaneous velocity just as it's hitting the ground, right? Which means we need to know, we're not given the time that it hits the ground, but we can find it, right? And so for part B, we first need to know, oops, we first need to know when the ball will hit the ground. And I'll just do a little arrow, which means find t. We know the distance equation, right? We said that s of t is the distance what if we force it to be 450 meters, right? Because that's the distance that it has to travel. And so now I'm forcing it to be 450, but I also know s of t is 4.9 t squared. Now I can solve for t, right? Because I've got 450 is 4.9 t squared. And so t squared, and I usually like to have whatever I'm solving for on the left-hand side. So I just swing it around and I get 450 divided by 4.9. So t, time has to be positive, right? And so I'm just going to use the positive root of 450 over 4.9. If I do 450 divided by 4.9 and then square root that guy, I get t is roughly 9.58314847 seconds. Yeah. Either way, it's fine. But usually it's easier to kind of wrap our heads around, even if it's a decimal approximation, right? The exact answer is great too, but I'm even going to round this to approximately 9.58 seconds. So now I've got a time that I'm interested in the instantaneous velocity at, right? And so now we can use v of t is 9.8 t and say that v at 9.58 is 9.8 times 9.58. Again, always showing that these are approximations. In fact, this is an approximation too, but pretending it's not. 93.884. And then because it's a velocity, right, we're talking about meters per second, which I didn't say in my other one, I think. I did. Nice. So these two problems that we just did, they're the same, right? We're finding the slope at some point, but if the function that we're talking about is a distance function, right, then the slope at each point is going to be the velocity. So now let's talk about derivatives. We've been waiting for this Or maybe you didn't know we've been waiting for this. But we have been. So the derivative of a function at some point a, right, we denote it by f prime of a. So here, let's write this down. So the derivative, oops, the derivative of a function f at a number a denoted by f prime of a, which you're going to read as f prime of a, is f prime of a is the limit as h goes to 0 of f of a plus h minus f of a over h, if the limit exists. If the limit exists. The only thing that's new here, right, is calling the slope at some point the derivative, right? But the slope at that point from now on is just going to be called the derivative. So just keeping track of those two are the same, right? So if you understand the concept of, okay, well, I'm finding the slope at this point, now we just need to make the connection and say, well, the derivative is the slope of the tangent line at some point. Make a little note of that here. The derivative is the slope of the tangent line at some point a. In fact, in the next section, we're going to extend it to just be any point, right? But all we do is replace the a with x, right? And then it allows for just any value of x. But for now, we're just going to talk about at a point. Let's do an example. So now I can ask you something like, find the derivative of the function, and then just give you a function. So find the derivative of the function f of x is x squared minus 8x plus 9 at the number a. So just leaving it open to be any value of a. We want to find the derivative. So what we want to do is we want to find f prime at a, right? That's the derivative of f at a. So here, this is the derivative of f at a. That's what that notation is saying. Which we just established is the same limit, the limit as h goes to 0, and then what we call that a plus h minus, or the f of a plus h minus f of a over h, it's called a difference quotient. Doesn't matter, but that's what it is the limit as h goes to 0 of f of a plus h minus f of a over h. It's when we get into these bigger functions, right, that I want to be really careful about separating my f of a plus h and then my f of a, because I want to make sure that I've got them both complete in there. And so I've got the limit in. In fact, I'm going to need a little bit more room, so I'm going to scoot it over here. Wait. I want the limit as h goes to 0. And I'll start with my f of a plus h, because wherever I see an x, I'm going to plug in a plus h. And so I've got a plus h squared minus 8 times a plus h plus 9. That's my f of a plus h. Minus f of a. F of a is a little bit easier because I just, wherever I see an x, I plug in an a. So I get minus a squared minus 8x plus 9, all in big brackets. And then over h. I'm going to expand this, simplify this, right? And what you'll see is that any term that doesn't have an h in it is going to dissolve, right? Or it's going to disappear. The limit as h goes to 0, I'll keep my square brackets a little bit longer, right? But then I get a squared plus 2ah plus h squared minus 8a minus 8h plus 9. What I'm going to do for my second chunk is I'm going to bring that negative inside, being really careful to put the negative on each of the terms. So then I get minus a squared plus 8x minus 9. If you find you get to the end and your h won't cancel, usually it's because you forgot to bring in that negative onto your f of a. So now I'm taking the limit as h goes to 0 of, okay, I've got my a squared minus a squared, can cancel those. I've got, what did I do? I have an x in here and I shouldn't. 8x should be 8a. Just little slip up. But I noticed because they weren't canceling, and I know they should be, minus 8a plus 8a. Plus 9 minus 9. Like I said, any term that doesn't have an h in it is going to cancel away. So now I take the limit as h goes to 0. All I'm left with is 2ah plus h squared over h. And just to emphasize that I have to have an h in both of the terms in the numerator, I'm going to pull it out. You don't have to. If you want to cancel it right away, that's fine. But I'm going to have h times 2a plus h over h. Thank you. Thank you. Just tack it on here. Nothing happened. Nothing to see here. Let me check against these. Okay, now I'm good. So now I can cancel these h's. Good thing I had an h on the 8. So now I can take the limit as h goes to 0 of 2a plus h minus 8, but all I'm left with it, if h is going to 0, is 2a minus 8. Nice.
So that's the derivative.
That's the derivative.
And can you like reverse it?
Yes, in Calc 2. But yeah, definitely. So we're only going to take the derivatives. Notice also that the function simplified, right? F of x was x squared minus 8x plus 9, right? So my highest power is 2, right? My derivative is always going to be lesser powers, right? So it's going to get smaller. And so f prime at a is 2a minus 8. But if I want to talk about f prime at x, it would be 2x minus 8, right? So now it's just a straight line. So it went from being some parabola to just a straight line, right? So it's always going to simplify as we go. Okay, so like we were saying, right, from here on out, instead of talking about the slope of the tangent line, we're going to talk about the derivative of f instead, right? But they mean the same thing. And so what we can say, the tangent line to y equals f of x, just establishing that we're talking about the function f, at a f of a, because that would be a point on this curve, is the line through a f of a. It's the line through a f of a, whose slope is equal to f prime of a, whose slope is equal to f prime of a, which is the derivative of f at a. So this is what we've said already, right? But now the only thing that's happening is we're replacing that slope of the tangent line with just calling it the derivative. But nothing else has changed. So if we want to do an example, if I ask you to find the equation of the tangent line, but let's use the same function that we just dealt with, right? The x squared minus 8x plus 9. So find an equation of the tangent line to the parabola y equals x squared minus 8x plus 9. I'll just make a note here, same as previous example. At the point 3, -6, right? I could have just said x equals 3, right? And then you could plug in x equals 3 into your y equation and solve for y, but what you're going to get is -6. So we already found I guess I should capitalize we already found that f prime of a is 2a minus 8. And so the derivative at a is the slope of the tangent line at a. And so now if I'm interested in the point 3, so therefore at a equals 3, f prime of 3 is 2 times 3 minus 8, putting me at 6 minus 8, which is -2. So now I know the slope at 3, -6 is -2. And I know the point that I'm passing through is 3, -6. And so put it on the same page here. Therefore, the equation of the tangent line is y minus, and you know what? Y naught equals m times, oops, x minus x naught. Oh yeah, sorry. Is that good? But why not? If we're talking about in terms of the function f, we could replace this little guy with f of a, and x naught we can replace it with a, and m we can replace it with f prime at a. Those are all equivalent and we can swap them out. And so now what our function is going to, or the tangent line is going to look like, is going to be y minus f of a is f prime at a times x minus a. Right. That's the same thing. That's the point slope form of the line. I know f of a is -6. I know f prime at a is -2 times x minus, and then a is -3. +3. I can simplify this. All right, I get y plus 6 is -2x plus 6. Moving the 6 over, I get y is -2x plus 6 minus 6. So y must be -2x. This is the equation of the tangent line. Equation of the tangent line. Oh. I don't know. I feel like they have a question or.
Yeah.
Oh, it's nasty out. Yeah.
Is this any kind of exam?
No, we're just hanging
I
out.
just came in and wandered around and then left.
Go for it.
I'm with facilities.
I believe you. No one else would want to check out the room.
I appreciate it. Sorry.
Do you mind if we do some calculus? Yeah. Oh, we lost the doorstop just this week. There used to be a doorstop and now it's gone. I can't
Is
find it.
open doorstop?
Yeah,
What
those
happens
tend to
typically?
disappear, right?
Yeah, it's when the fire department come on around and do an inspection, they see those, they pick them up, and then they'll go into the next building and throw in the trash.
Oh,
It's,
fire hazard, I'm
yeah,
sure. Yeah.
The the doors have got to be able to close on their own, and they're not to be wedged open, just in case. So
I guess we're safer.
yeah.
Makes it awkward when you come late to class. So you have to open the door. All right. What were we doing? Now I want to talk about the snow and door stops and not this. Anyways, so we've got our equation of the tangent line, right? We had to find the slope. So remember, the derivative is the slope. Like, just watching. Right, the derivative is the slope of the tangent line. And what we're going to say is that the derivative is the instantaneous velocity if we're talking about velocities and speed and such, right? And so what we're going to talk about is the derivative is the instantaneous rate of change. And then if we're talking about the secant line, right, so the tangent line just touches at one point. The secant line we already established was the average rate of change, right? And so the derivative oops, f prime of a is the instantaneous rate of change. Hey, no problem. Instantaneous rate of change of y equals f of x with respect to x when x equals a. Like I said, in the next section, we're going to take this and just talk about in general for x's. So then we're not just talking about some x equals a, right? But the shift won't be that bad. The slope of the tangent line, or sorry, the slope of the secant line is the average rate of change. Is the average rate of change. Right. To make a secant line, we need to have 2 points, right? Some point A and B, or A and A plus H if we want, either way. So what this looks like is we've got some curve here. Wait, whoa. Let's say like this, mix it up a bit. Then if I'm talking about some point P and some point Q, like we said before, in the very beginning of this chapter, right, when we started talking about limits and we were moving Q closer to P, right here, let's talk about x1, x2. The y value at x1 is f of x1. The y value at x2 is f of x2. Here, let's see. So here, the pink line is going to be the instantaneous rate of change. is the slope of the tangent line at P, which is just f prime at x1. All those things are going to be the same. Whereas if we're talking about, or maybe I'll use a green line or something. How can I connect these two? Maybe like that. Green's hard to see here. I didn't really pass it through the lines. Use a darker green. Then the green line is the average rate of change which is the slope between P and Q. So it just depends on if we're talking about the instantaneous rate of change or the average rate of change. Right, the average rate of change, then we're talking about 2 points, and then we just use the rise over run, right, the slope between P and Q. The instantaneous rate of change is going to be the derivative, right, which is the slope of the tangent line. Any questions? Yeah. Yes. And with a little bit of luck, we're going to do it today. So, but maybe it's more than a little bit of luck. Got a ways to go. But nice. I know you guys can't wait to get into the second derivatives. Go, go, go. We will. We are going to get into leaving limits behind, sort of, the last section of chapter 2. So 2.8 is the derivative as a function Right, we already said that, well, it's not that big of a stretch. If I'm able to find f prime at a, couldn't I just replace a with x and just have a general function with respect to x? Yes, you can. Yes, we can. So in the previous section, which we just did, we found f prime at a, the derivative at a point A, right? So it's the specific point A. The derivative at a point A. In this section, we want to find f prime of x. We want to find f prime of x for any arbitrary x. For any arbitrary So what we say is we have f prime of x is the limit as h goes to 0 of, you guessed it, f of x plus h minus f of x over h. Not that different. This is called the derivative of f. It's called the derivative of f with respect to x. definitely put a box around this here. This is what we call the limit definition of the derivative. The limit definition of the derivative. Should have squeezed that on there, but anyways. Can put it below too. Oh. Starting next day, we're going to look at ways that we can find the derivative without using the limits, but at its core, it uses limits, and so that's why we spend time talking about limits, right? But there's rules that we can use to find derivatives and just kind of bypass the limits, right? They're happening in the background, but you can always fall back to the limits, right? But the reason those rules were invented was to not have to find the limits all the time. And so, but on test 2, which is after reading break, I know, you will have to use the limit definition of the derivative to find the derivative. Right? And so you will have to use this. So let's do an example. If we let f of x be x to the power of 3 minus x, I want us to find f prime of x. I guess call this part A, and then I want to do another part B where we're going to compare the graphs of f and f prime. First thing we're going to do is we're going to find the derivative. And so what we said was, well, if I have f of x, I can find f prime of x by just taking the limit as h goes to 0 of f of x plus h minus f of x over h. Should feel pretty familiar now. All we've done is replace the a's with x's. So now we're going to take the limit as h goes to 0, and I'm going to use my big square brackets because things are going to get messy, right? X to the power of 3 minus x, but replacing the x's with x plus h. Ugh. Right, and so I have x plus h to the power of 3 minus x plus h, square bracket, minus, and then f of x is just x to the power of 3 minus x over h. Same as before, right? I'm going to expand this. I'm going to put a lot of work into it, but what's going to happen is anything without an h will likely just fall out and cancel, right? So that's what I'm working towards. And so I'm going to have the limit as h goes to 0, always out front, of, and here we go, x plus h times x plus h times x plus h. And like I said, you will probably be faster than me at expanding it, right? Because I do 1, 2, 3, and then I expand it another time. But better safe than sorry. Minus x plus h minus x to the 3 plus x if I'm dissolving those brackets. May as well do something over there in that corner, right? May as well bring in that negative over h. So I want the limit as h goes to 0 of, I get x squared plus 2xh plus h squared times x plus h minus, I'll bring the negative inside here, minus x minus h minus x to the 3 plus x all over h. Limit as h goes to 0, and so now I'm expanding again, and so I get x to the power of 3 plus x squared h plus 2x squared h plus 2xh squared plus, and I'm going to keep the x's in front of the h's, and so I get plus xh squared plus h to the power of 3. Oh, I ran out of room. I can cheat and move it over, so I will. Then minus x minus h, then minus x to the 3 plus x over h. Hopefully I didn't forget anything. I'll cancel and see what happens. X to the 3 is going to cancel, minus x to the 3 plus x minus x, phew. And then I can probably collect a few things here. So I get the limit as h goes to 0 of x squared h plus 2x squared h. So I get 3x squared h plus 2xh squared plus xh squared. So plus 3xh squared. I'm gonna dock these as I go. This one and this one's gone. This one done. Because I forgot that other one that last time. Plus h to the 3 all over h. Oh, my h always goes to a triangle. Oh, now we can cancel that h, which is the troublemaker all along, right? And so now I can take the limit as h goes to 0. I'll pull out that common h just to make sure that it's all in each of the terms, but 3x squared plus 3xh plus h squared over h. I was going to use that overhead projector next week. I'm kidding.
Okay. That was my biggest fear. Even though it looks an antique, someone still does use it. But,
oh, really?
uh,
Hand would get smudgy.
yeah. And then again, sorry.
No, no worries.
This will be the last. You can think of me as stage. You're not free radical. Once I've taken this.
H just got canceled though.
Is that
Yeah.
H can go home?
H can go home.
Sorry.
No worries. So now.
Where did you get the 3x squared h?
Oof. Oh, x squared h plus 2x squared h is 3x squared h. Because I'm collecting like terms. Yeah. And that's why I had to dock them more because I collected them, not because I canceled them. Yeah, yeah.
So you're still there, minus H.
Yes, I did it again. Thank you. Oh, I think I can just tack it on, right? Phew. Sort of. It's bad that I keep forgetting it, but hopefully you won't do the same. And you guys are staying on top of it.
The same.
Oh, and you're like,
So yeah.
Thank you. See? You guys are Let me check against the ones that I actually spent time on here. 3x h plus h squared minus 1. Looks good. Thanks, guys. Now I want the limit as h goes to 0. I'll just write it out because I've been blubbing it everywhere here. 3x squared plus 3xh plus h squared minus 1. If I let h go to 0 here, 3x squared minus 1. Again, right, we moved from a power of 3 to a power of 2. So you always want to make sure that when you take the derivative, more often than not, it'll just become a simpler function. Right? But notice here, right, that f prime of x is also a function of x. Right? So now it moves across the x-axis, and I can kind of work with it that way. So part B was to compare the graphs, because it was a long time ago that we wrote it, of f and f prime. And what I'll do is I'll just take us to Desmos first here, and where is it? Here. I already plugged them in, x to the power of 3 minus x, so the red curve is our f of x, and then our 3x squared minus 1, that's our derivative, right, f prime of x. And so what you'll find, the red curve, right, is this power of 3, right? And so we've got this kind of wavy thing going on, and then we've got this parabola. And so what I want you to look at, though, is at these points of the maximum and the minimum, those are the easiest ones to pinpoint, because here, if we think about the slope at these points, the slope would be 0, right? Because if we've just got a straight line here, then the rise is nothing over however big you want to make it, right? It's always going to be 0. So here, the slope is going to be 0, right? And also up there, the slope is going to be 0. If blue is the slope of the tangent line at each of these points, well, where I've got a max or a min, right? So where I've got this bottom of the barrel or top of the hill here, that's where I'm going to be crossing the x-axis, right? And so here I go, my derivative is going to be 0, right? And so, and also here, right, I'm crossing the x-axis again. And we can also do things like, okay, well, here, I can figure out what the slope of the tangent line is going to be, right? Because I know the function for the derivative is 3x squared minus 1. And so if x is 0, then 3x squared minus 1 is going to be -1, and that's why I'm at -1 down here. What's another thing? Here, right? I'm increasing. We talked a little bit about increasing functions, and it's not that weird, right? If you've got this kind of positive slope, right, then for all these values of x, all the way up until this point, we should be above the x-axis, right? We should have positive values of y, because the y's are the slopes, and they should be positive, right? After this point, we start going downhill, 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 up to here, right? And so here, we've got these negative slopes, right? Never mind that it's increasing or decreasing and increasing, right? They're all negative down here. Right? And then from here, at this point, our slopes are positive, which makes sense because from here, right, this is where we change and we have positive outputs of y. And so the key things, right, are just the general slopes. Are they positive or negative? That's going to tell you if you're above or below the x-axis. And then where you've got these slopes of 0, right, where the tangent line would have a slope of 0, so the minimum and the maximums, those are where you're crossing the x-axis. What happens in between is maybe not necessarily as obvious, right? But you need to figure out those points where we're going to cross the x-axis, right? That's where you've got the min and the max, and then if it's going to be positive or negative. So let's kind of do our best to copy that over in here. So if we have a look at f of x equals x to the 3 minus x, like I said, I'll do my best, but no guarantees here. X and y. Feel like it looked something like not really like that, but I did it as a smooth curve. So if I delete, or if I remove one, I remove it all. Hey, not bad. If we think about here at this point and this point, we know that f prime of x will be 0. And f prime of x will be 0. Oh. So if I draw another one here, f prime of x, we said was 3x squared minus 1. If I try to replicate this curve here, add that same value where sort of same, I guess. This is where I'm going to cross the x-axis. So I know those 2 points. Another point that I know is that, well, at here, x equals 0, and f prime at 0 is -1. Because I can just use the f prime function, use 0, and I find that it's -1. And so down here, I'll put it somewhere here at -1. I know the general shape of my parabola, right? And because it's positive, I know it's pointing up, but also here, I've got these positive slopes. Positive. And then between these 2 points, it's going to be negative slopes. And then from this point, it's going to be positive slopes again, which matches what we're expecting, right? We've got this parabola, and I know it's going to stop at -1. So what it's going to look like might be something like this. Just to highlight that for all these values, positive f prime of x, and down here is where we have negative f prime of x. out of time or what? I am too. We'll start with the next example next day. Cool. Any questions? All right. See you guys on Thursday. Bye, guys.